Okay, fine. Once again, good morning to all. In last class, we have discussed regarding the per unit system. Okay, if we have a different per unit systems, that means if we want to change the per unit of of one base to another base, or if you want to find out the per unit of an given power systems. Okay, how we are going to do, how we are going to solve. We have seen a couple of sums also. Today's class we will go for the single line diagram. Okay, we will see the single line diagram, and from the single line diagram we are going to finding out the impedance diagram and the reactance diagrams. Okay, those diagrams are used in different studies. That means for fault analysis or for load flows, we have to draw the impedance and reactance diagrams. Okay, therefore from the single line diagram we are going to drawing the impedance and reactance diagrams. Okay, therefore first of all, what do you mean by single line diagram? Okay, what do you mean by single line diagram? Okay, generally our power systems, okay, our power systems is a three phase. Okay, therefore we are going to having a three phase system, three phase four line system, two phase three line system. Okay, the for that power system, if you want to find out, or if you want to go for a load flow studies, for a three phase it will be a somewhat complex. Okay, therefore we are going to instead of finding the fault analysis or load flows for a three phase system, we are making it a single line. That means we are taking as a single phase. Okay, we are taking as a single phase. Yeah, if you since our power system is a balanced network. Okay, therefore if we have a single phase power, by multiplying with 3 we are going to getting a three phase power. Okay, therefore since it is a balanced system, we can simply multiply by 3. Okay, simply by multiplying with 3 we can get the three phase power, three phase system. Okay, uh, yeah, number 274. Okay, single line diagram. Okay, in our power system, okay, in our power system we are going to converting the three phase system. Three phase system has a single line. Okay, therefore how we are going to draw this single line? Okay, how we are going to drawing the single line means, by you, first of all going to single line, you have to know the some symbols. Okay, symbols, how we are going to representing those elements in our power systems in a single line diagram. Okay, if we have any rotating missions, that means it may be an induction mission or it may be a synchronous mission. Okay, if we have any rotating mission, it has to be represented by a circle. Okay, it will be represented by the circle. Okay, if two winding transformer means it will be represented as similar to a transformer. Okay, this is a three winding transformer. Fuse will be represented in this manner. Okay, fuse, this is a current transformer. Okay, current transformer is used for measuring the currents. Okay, currents in the transmission line. Okay, and a potential transformer. Okay, if we have a potential transformer, it will be used. Okay, symbol like that. A single line diagram. Okay, in single line diagram, first of all you have to know the symbols. Okay, how we are going to represent the different circuits. Okay, different symbols in our power systems. Okay, how we are going to representing the different symbols. Okay, most of the symbols already you have come across in emissions and power systems. Some symbols like circuit breakers. Okay, circuit breakers, the air arc breakers. Okay, it may be your transformers, delta connection, star with grounded. Okay, these meters are you have known. Okay, now we will take our power systems. Okay, we will take the power system, how we are going to drawing these by using these elements. Okay, we will see it. Okay, let us take a power system having some generator. Okay, this is a single line diagram. Okay, this is a single line diagram. That means single line diagram means it is only a single phase circuit. Okay, it is only a single phase. Okay, generally we are going to having a three phase circuit. For analysis point of view, the three phase circuit will be somewhat complex. Therefore we are reducing it into a single phase. Okay, we are reducing into a single phase, and we are going to performing our analysis.
Okay, and after analysis, if we require a three-phase data, we are simply converting into a three-phase. Okay, if it is a balanced network, simply by multiplying with three, we can convert into a three-phase. Okay, therefore it won't be a much problem. Yeah, therefore this is a single line means it will be a single phase only. Okay, single phase diagram. Therefore it is a generator. Okay, a generator is a rotating machine. Therefore we are going to representing by a circle. And the symbol, okay, the symbol represent that it is a star connection with grounded. Okay, and these are the ratings of your generator. Okay, ratings of your generator. And this is nothing but your circuit breaker. Okay, this is nothing but your circuit breaker. Okay, and this is a two winding transformer. Okay, two winding transformer with the primary star grounded and secondary is a delta. And this is a circuit breaker, and this is also circuit breaker. In between this one they had mentioned the ohms. That means this is the transmission line. Okay, this is the transmission line. A simple transmission line will be represented by a single line. Okay, therefore this is a transmission line having some impedance. Okay, having some impedance. Okay, and similarly this is also another line of a generator, a circuit breaker, transformer, and connected to a bus bar. This is nothing but a bus. Okay, where two or more lines are connected. Okay, from the bus again we are going to connecting to a circuit breaker. Between the circuit breakers we are having a transmission line. Okay, this is a transmission line too. Okay, we have a transmission line too, and then we are going to having the transformer, which is a delta and star connections. And we are going to having this is a load. Okay, here we are considering the load as an induction motor. Okay, that is nothing but a load. Okay, in some cases here also we can take the bus, and we can take the different loads connected to the bus. Okay, in this circuit we are taking a single load, therefore we didn't connect any bus. If we have a more number of loads, then simply we are going to connecting a bus, and we are going to connecting the loads. Okay, therefore this how we are going to draw the in exam they will give the single line diagram. This diagram they will give. Okay, if by seeing this diagram you have to calculate the fault analysis. Okay, that means you have to draw the first of all you have to draw the reactance diagrams and the impedance diagrams. After drawing the reactance and impedance diagram, then after you are going to calculating some y bus, z bus. Okay, those we have to calculate. Okay, therefore initially in per unit systems you are going to see this type of circuits. Okay, single line diagram, you are going to see the single line diagram. Okay, from this single line diagram, from this single line diagram you are going to calculating the whatever the required. It may be a fault analysis or it may be a load flows, everything we are going to perform. That means this is a power system. Okay, this is a power system having different loads. Okay, having different loads. Okay, different components, having different components. Okay, once again I am saying still in chat box I am getting the messages like voice is breaking. For 1 or 2 days please adjust for this one. In college there is a network issue, that's why I had changed the place also. uh, I had sitting I had taken another room, but still you are getting the same problem. In college there is some small network issue, that's why you are facing this problem. Okay, try. Mm. Now from this one, okay, from this one, how we are going to calculating the impedance diagram. Okay, we will see that how we are going to calculating the impedance diagram for a single line circuit, single line diagram. Okay, actually you know that how what is a single line diagram. Okay, I had mentioned here also. Okay, generally our power system is a three phase, but for making it simplify, we are going for a single line diagram. We are using the single line diagram. That means simple our power system we are going to represent in a single line. Okay, from the previous knowledge you can calculate the per unit for each and every device. Actually here they had given, okay, whatever the values they had given, those values are the actual values. Okay, those values are the actual values. Okay, these are the actual values. Yeah, now you can convert into a per unit system. Okay, actually they didn't give any base values. You can take the base values of your generator. Okay, these values as the base values. Okay, you can take it as a base values, and you can convert. Okay, you can convert this 100 ohms into a some per units. Okay, you can convert into a per unit. Okay, that may be your first task. Okay, from the up to whatever the knowledge you have up to now, by using that knowledge, you can convert this entire power system into a per unit system. That also we will see it. We will see it. Before that one, we will see the in what do you mean by impedance diagram, how we are going to drawing the impedance diagram, and what is a reactance diagram, how we are going to drawing this reactance diagram, that we will see. Okay. We will see it. Okay, fine. Coming to the impedance diagram. Okay, impedance diagram is mainly used in load flow studies. Okay, impedance diagram is used in load flow studies. Okay, next topic. Okay, that is your second chapter, maybe a load flow studies. Okay, you are going to use different methods for performing the load flows. Okay, we will see what you mean a load flows, or we will get come across the next chapter. Okay, especially in load flows, we are going to draw the impedance diagram. Okay, actually I said no, first chapter is the basics for your PSA. Okay, entire PSA, what are the concepts you require, that concepts you will get in your first chapter. Okay, therefore this impedance diagram, okay, this impedance diagram you have to draw while you are performing the load flows. Okay, while you are performing the load flows, you have to draw the impedance diagram. For drawing this impedance diagram, we will make some assumptions. Okay, we will make some assumptions. That assumptions are nothing but the first assumption. Okay, the first assumption is the impedance offered by the synchronous generator connected to the neutral to ground is generally neglected. Then what it means, generally in a single line diagram you have seen. Okay, in single line diagram you have seen that there is an star connector which is connected to the grounded. Okay, generally the star connector which is connected to the grounded, it will be grounded by using some resistance, or it may be grounded by using some inductance. Okay, which we all we come across in our power system. So why we are going to connecting our, this is a generator. Okay, this is a generator which is a star connected. It may not be directly connected to the ground. It may be grounded by using some resistance or inductance in order to limit the ground fault current. Okay, when there is an no, a ground fault occurs if in a generator, that means some phase maybe touches to the neutral, there will be a huge amount of current flowing in the circuit. In order to limit that currents, we will use this some resistance, or we may call it as a Peterson coil. Okay, we are going to using some techniques. I think so you may come across in power systems too, or it maybe comes in further. We are going to using some impedance in the ground. Okay, that means neutral to the ground. Okay, this is a neutral connection. Okay, this is a star connection, means we have a three-phase alternator. Okay, this is a three-phase alternator. This is the neutral. Okay, neutral point will be grounded. Okay, will be grounded. Okay, this is an alternator. Okay, in between grounding we are going to place some resistance or inductance. Okay, we are going to having some impedance here in order to limit the fault currents when you occur the line to ground faults. Okay, that means suppose this phase is connected to the ground. Okay, there will be a huge amount of current flowing in this circuit. Okay, in this circuit, in order to limit that fault currents, we are going to placing the resistance. Okay, that's why in order to overcome this one, we are going to placing this resistance. The first assumption is those impedance. Okay, those impedance we are going to neglecting. Okay, that means if there is any impedance in a synchronous generator from neutral to ground. Okay, neutral to ground, if there is any impedance, that impedance we are going to neglect. Okay, and second one is the magnetizing current in the transformer, it will be neglected. Okay, such that magnetizing branches, shunt branches are neglected. Okay, that means already you seen in the transformers. Okay, you have seen in the transformers, there will be an under no load condition, or it may be under load condition also, there is a shunt branch elements. Okay, shunt branch elements and a series branch. Okay, this shunt branch, it is drawing the no load current. This no load current will flows to the having two components, magnetizing component I mu and IE. Okay, active component. You may have the two components. This magnetizing component will be very less when you are considering regarding the load connection. Okay, this no load current will be very small when you compare with the load condition. Therefore, this component is going to be neglected. Okay, this no load current will be neglected, and if we neglect this current, we can neglect this branch. Shunt branch can be neglected. Okay, therefore, in transformers, the shunt branch is going to be neglected while you are drawing the impedance diagram. Okay, only we have a series branch. Therefore, simply generally transformer having the series and shunt branches. Okay, series and shunt branches. Okay, the shunt branch is neglected. Therefore, only for the transformer we have a series branch only. You don't have the shunt branches. Okay, therefore these two are the assumptions. Okay, while you are drawing the impedance diagram. Okay, in reactance diagram we may add the one more uh, assumption also. But for impedance, we are going to assuming these two conditions. Okay, these two conditions. That is the shunt branch of the transformers and the neutral to ground impedance are going to be neglected. Okay, these two are going to be neglected. Okay, keep in mind that you have to consider these 2 points. Okay, now I am going to show you different components. Okay, different components in our electrical systems. How we are going to draw the impedance diagrams. Okay, so first one is the generator. Okay, for a generator, you are going to representing in the with a series inductor, resistance, and a voltage. Okay, and we are going to having the voltage E. Okay, okay, in same fashion. Okay, here I have taken in this manner. It may be a series branch like this also. It will look, both will be equal. Okay, therefore we will have some synchronous impedance. Okay, these two are the synchronous impedance along with the voltage developed by the generator. Okay, here you can see that phase and neutral. Okay, because it is a single line. Okay, we are going to representing a single line diagram. Therefore it is a per phase only. We are going to representing the components in per phase only. Okay, these are the phase components. Okay, therefore phase to neutral. Okay, this is the equivalent circuit of a generator in uh, equals. Wait a minute. Wait a minute. Mhm. Okay, fine. Generator. If you want to represent a generator in impedance, that means in previously you have seen the generator. Single line diagram has seen the generator and a transformer. This generator will be replaced by a series elements or like this. Okay. Therefore, this is your generator. In place of generator, you are going to draw the impedance diagram. Okay, impedance diagram like this. Okay. And coming to the second one, transformer. Okay. As we discussed in second assumption that the shunt branch elements of the transformer are going to be neglected. Therefore, only we are going to having the series branch elements only. Okay, if it is a combination of resistance and reactance. Okay, only we are going to having the series branch. Shunt branch we are going to neglected. Okay, the shunt branch are going to be neglected. Only we are going to having the series branch. Okay, therefore this is regarding your transformer. And coming to the transmission line. Okay, how we are going to representing the transmission line. Okay, transmission line means simply it is a straight line in single line diagram. Okay, if you want to draw the impedance diagram, the transformer you are going to transmission line you are going to take consider as a pi model. Okay, it is a pi model. Okay, already you come across in power systems too. Okay, for a medium transmission line, for the medium transmission line you have a T model and pi model. Okay, you have a three transmission, short, medium, and long transmission lines. Okay, therefore this is nothing but a pi model. Okay, in impedance diagram we are going to representing in the pi model. Okay, this is your how we are going to represent the transmission line. Okay, and next one is the synchronous motors. That means it may be a synchronous motor, it may be induction motor, whatever may be. Okay, a load. Okay, simply it is a load. Okay, if it is a load, then it will be represented in a combination of similar to your generator. Okay, a generator, this E is nothing but a generated voltage. Okay, here this is nothing but a back EMF. We are going to call it as an EB. Okay, in motors. Okay, in motors you are going to having the back EMF. Okay, already I think so you have completed the missions and you know that what is the back EMF. Okay, therefore it is having some impedance in combination with the a back EMF. Okay, therefore the figures will be look like same. Okay, the generator and the motor will be look like the same fashion. Okay, these are the most of the elements which you are going to get in your single phase diagram, a single line diagram, which you are going to converting into a into impedance diagram. Okay, while you are converting in impedance diagram, you have to remember all these diagrams. Okay, if you remember all these diagram, then inductive loads. The next one is the inductive load. Okay, simple inductive load. We are going to place an inductor having combination with a resistance. Okay, inductor means internally it will have the resistance. Okay, two load. Previously we have seen the motor load. If it is an inductor load, simply we are going to represent it by an impedance. Okay, now, okay, here I have taken a small example. Okay, I have taken a small example how to represent the single line diagram, the single line diagram in impedance diagram. Okay, how we are going to representing the single line diagram. This is a single line diagram. Okay, actually for the single line diagrams, first of all you have to convert into per unit systems. Okay, and then you are going to draw the impedance. Okay, in problems we will get more information regarding this one, but at present, okay, at present, see how we are going to represent. This is a generator. Okay, this is a generator. Therefore generator will be represented here. Generator will be this is a generator part. Okay, generator will be represented as a series impedance and then voltage source. Okay, series impedance and a voltage source. Okay, therefore this is a generator. Okay, after generator we have a transformer. Okay, we have a transformer. Okay, therefore transformer we are going to represent it by a series elements only. Therefore R and L. Okay, series elements of R and L. Okay, and then after transformer, here we have a transmission line. Okay, here we have a transmission line. Therefore transmission line will be represented by using pi model. Okay, therefore transmission line we are going to representing by using pi model. And then again we have a transformer. Therefore transformer is going to be representing, and then we have an inductive load. Okay, here they I have not mentioned any motor. If I make a circle and if I mention it like AM, then it is a motor. Then we go for the motor connection. Okay, simply directly I have given a straight line. Therefore it is an inductive load. Here we have a load. This symbol, okay, this grounded symbol will indicate that there is a load is connected here. Okay, therefore there is a load here, has similar here. Okay, therefore there is a load. Now we are going to representing the load circuit. Okay, if it is a motor, if I mention it motor, then you are going to place the back EMF here. Okay, we are going to having the back EMF E. There is a voltage source E. Okay, if it is a motor. Okay, therefore this is how we are going to converting the a single line diagram to an impedance diagram. Okay, single line diagram to an impedance diagram. Okay, and while coming to the reactance, diagram, one more assumption will be added, that is what are the assumptions we have seen now. Okay, the same assumptions with along with assumptions, there is one more assumption, that is we are going to neglecting the resistance. We are going to neglecting the resistance. Therefore, if we want to draw the reactance diagram, we won't have this resistance. We won't have the resistance. Okay, we will see it in detail. Okay, therefore keep it in mind. Okay, both will be the same. Both will be the same. One more assumption will be added for a reactance diagram. Okay, therefore this is regarding to your impedance diagram. Okay, how from a single line diagram. Okay, up to now we have seen that what do you mean by single line diagram, what do you mean by single line diagrams, and different symbols we are going to use in the single line diagrams, and what is an impedance diagram, where we are going to use this impedance diagrams, and how we are going to draw the impedance diagram for a single line diagram, that we have seen. Okay, up to now if you have any doubts you can ask. Okay, wait a minute. Okay, fine. Okay, up to now, if you have any doubts, okay, regarding the impedance diagram, if you have any doubts, you can post it in the chat box. Okay. Next, I am going for the reactance diagram. Okay, I am going for the reactance diagram. Okay, what are the assumptions? Okay, especially this reactance diagrams will be used in fault calculations. Okay, this is used in the fault calculations. Okay, previous one, the impedance diagram is used in load flow studies. Okay, previous one is used in load flow studies, and this is used in the fault calculations. Okay, this is used in the fault calculations, that therefore where we are going to using all these circuits, we have to remember in fault calculations we are going to use the reactance diagram. Okay, And the same assumptions which we have seen in the previous same assumptions, along with those assumptions, we are going to considering the one more assumption, that is this one. Okay, line ground capacitance are neglected. Third point and fourth point. Okay, capacitance and the resistance. Okay, in our circuits are going to be neglected. Okay, capacitance and resistance. Therefore, in transmission line, where we are going to use the pi model, there the capacitance can be neglected in the reactance model. Okay, these two assumptions will be added. Okay, these two assumptions is going to be added. Ground capacitance and the resistance, okay, are going to be neglected. Okay, therefore, if you observe the symbols, a three-phase generator. Okay, in previously for an alternator we have seen the resistance here. Okay, now there is no resistance. Okay, similarly for motor also. Okay, it may be a synchronous motor, induction motor, whatever the motor. Okay, motor also previously we have a resistance here. Now the resistance is eliminated. Okay, transmission line, previously we have a capacitance here. Okay, pi model. Okay, we have a pi model, but in reactance we are going to neglecting this ground capacitance also. Only we have a series branch. Okay, oh, sorry, for transmission line. Okay, this is a transformer. Transformer we are going to having a series resistance and an reactance. This resistance is going to be neglected. For the transmission line, we will have the capacitance. Okay, in impedance diagram, we are going to having the capacitance. These capacitance are going to be neglected. Okay, these capacitance are going to be neglected. Okay, only we are going to taking the series element. Okay, therefore, further two more assumptions, that is shunt capacitance and the resistance. Okay, resistance and the capacitance are going to be neglected while you are drawing the reactance diagram. You have to assume these two more assumptions when compared with the impedance diagrams. Okay, therefore, now we will see a diagram. Okay, a small problem. How we are going to drawing the reactance diagram. Okay, as similar to the previous case. Okay, generator. In generator, we are going to replace with a generator equivalent circuit where we are omitting the resistance because it is a reactance diagram. We should not write the resistance. If we write the resistance, then it may convert it into impedance diagram. Okay, therefore this is nothing but your reactance. Okay, and similarly for a transformer also the resistance is eliminated. Okay, and similarly for transmission line. Okay, transmission line shunt capacitance are eliminated. Okay, these are eliminated. Okay, and transformer series resistance is eliminated, and load also, inductive load series resistance is eliminated. Resistance and capacitance are going to be eliminated, and we are going to replacing with equivalent circuit, so that we are going to getting the reactance diagram. Okay, this reactance diagram is used in the fault calculations. Okay, we may get a LG fault, LL fault. Okay, we may get a different types of faults. By calculating the fault currents, there we are going to using this reactance diagrams. Okay, an impedance diagram in load flows. Okay, in next chapter we may have the load flows. In load flows, we are going to use the impedance diagram. From the single line diagrams, we are going to draw the impedance diagrams and the reactance diagrams. After drawing the impedance and reactance diagrams, we will go for the calculations for calculating the different parameters. Okay, that we will see in the later classes. Okay, up to now, what we have discussed is what do you mean by impedance diagram, what do you mean by reactance diagram, and what do you mean by a single line diagram. Okay, all these things we have seen. Okay, up to now if you have any doubts. Okay, up to now if you have any doubts, you can ask it. Okay, regarding the per unit system. Okay, all basics we have seen. Okay, regarding the per unit system, single line diagram or impedance diagram and reactance diagrams. Okay.